Hi, today we're going to talk about an application of the kinds of differential equations that we have been studying. And this is one that you will see in physics if you take engineering physics or even general physics. A lot of times in either of those classes, they don't actually solve the differential equations because differential equations is not a prerequisite for those classes. But a lot of times you can find the differential equations in the textbook. And so what we're going to talk about here is how the solution functions that you might get in those physics textbooks, where they come from in solving the differential equation. And the idea is that the more you understand about the math that kind of goes on behind those formulas, the more you're able to really understand what those formulas mean and what the constants mean that you're working with. Okay, so our textbook introduces this idea at the very beginning of chapter 5. We didn't really talk about it yet. We kind of just jumped into the math part, but we're going to talk about that now. All right, so we know that whenever we use mathematical modeling to describe some situation that we want to clearly state our assumptions, define our variables, and all kinds of things like that so that we make sure that we are clear about what our model is actually describing. All right, so what we are going to be modeling here is this situation stated here in our assumptions. We've got a spring fixed at the top, hanging at rest. So that's what we see here in our first picture. Just a spring kind of attached to something, another part or a ceiling or something like that. We've got an object attached to the other end of the spring. So that's what's here in this second picture. And that will pull that spring down a little bit. And so that's a parameter. It's a constant. It's going to be different depending on the spring and how heavy that thing is that we attach to that. But this is going to be called L. It describes there in that second bullet point. This will pull the spring down an additional length L. And when we use our model here, we're going to describe the position of the object as a function of time. And so you can use whatever letter you want, H for height or X or Y or whatever. Our textbook usually uses X or Y. I'm going to use Y here since I've got this set up vertically. And so we're going to put this mark, we're going to call that our Y equals 0 point. That's when the system would be in equilibrium. So it's just hanging there, not moving, right? So everything's in equilibrium, nothing's moving, nothing's changing. And then what we want to describe is what happens after the object is set in motion. So there's a couple ways that might happen. You might hit the object with something, some other part might impart some kind of force to that object. Initially, we're going to just talk about basically you pull that object down a little bit and release it, or pull it down and give it some kind of velocity. We are going to choose to use positive Y as the down direction. That's what our textbook does, but that's just a choice that you make, and you all know that from taking physics, that you can choose the negative direction to be down or the positive direction to be down. All right, so that is our system, and then what we're going to start with is free motion. So we assume that there are no forces external to the system acting on the system once it is set in motion. So later in these notes, we are going to talk about forced motion, where there is some kind of continuing external force, maybe another part that is moving in the same system and imparting kind of a continuing force to the system. All right, so let's look at setting up the differential equation here. All right, so we've got three forces within the system. So we have the weight of the object due to gravity, and we're going to use G equals 9.8 meters per second squared, or if you are in the US system, we'll have 32 feet per second squared. All right, so then we also have the restorative force of the spring. So you can imagine if you pull a spring out and you let go of it, that spring is going to want to pull itself back to that equilibrium position. So that's what this is describing here, this restorative force of the spring. This equation that we have here comes from a law that you might have seen if you've taken physics before, called Hooke's law about springs. And often in physics, that equation for that law will be written F equals kx, where F is the force imparted by this spring. We've got several forces here, so I didn't want to just use F, I used R. K is that spring constant, and that will be larger for very stiff springs. If it's really hard to pull, that would have a large K value, and then really loose springs would have a low K value. X is the displacement. And so because we have this spring that's being pulled by the mass that's attached to the bottom of it, L distance, and then I used Y to represent whatever other distance here, that's what the Y plus L represents, is the displacement from the natural length of the spring. All right, and then we have one other force that might be part of the situation here, a damping force. And so this is some kind of resistance like friction would be, and we are going to assume in this model that that is proportional to velocity. So our problems that we're going to work on in the textbook and the homework, I'll use this word called damping. But what that has to do with is just basically some sort of internal resistance for the system, so maybe friction or something like that. Okay, so this damping force is assumed to be proportional to the velocity. So I have another constant here, damping constant. The problems that we will do either give you that or give you enough information to figure that out. And then because that force is proportional to velocity, we've got C times V for that force. Okay, so deriving the differential equation here, I've just typed a couple of kind of pieces of that, none of which exactly look like a differential equation, but we're almost there. All right, so the total force on all of the objects, we've got the weight due to gravity, that's acting in the downward direction, so that's going to be positive in our model because we've used the positive direction as down. The restorative force of the spring, I've got a minus in front of that, because that's wanting to pull that object back up, and then the damping force that is resisting motion. So remember that velocity could be positive or negative if it's moving down or moving up, but that's going to resist that motion, so it's going to be acting in opposition to the motion, so that's why I have a minus sign in front of that. All right, so in the next line there, we've just rewritten kind of each of those different terms. So force is mass times acceleration. That is just Newton's law. Force is mass times acceleration. That's the total force on all of the system. We've got the weight due to gravity, so mass times g. And then we've got the restorative force of the spring from up above. That comes from Hooke's law. And then the force due to damping, so CV there. So all I did was replace the different parts of that equation with what we had already talked about. And then in the next line, I've just rearranged some terms, maybe not in a way that seems immediately obvious, but this leads to our differential equation. All right, so remembering that we had a dependent variable y, which is the position of the object, that'll be measured in units of length at time t. And so we've got a couple of derivatives here, even though they may not be apparent in this equation you're looking at. So if y is our position at time t, then the first derivative, y prime of t, that's going to be the velocity. And the second derivative is acceleration. All right, so that gives us our differential equation here. I've got mass times acceleration plus c, remember that's a constant, times velocity, plus k, that's another constant, times y, equals, all right, and then mg minus kl. So I'm going to scroll back up here for just a second and talk about the picture that I kind of had there at the beginning. G, K, and L are all constants. They're not variables, they're all constants. And the important idea here is that the object is in equilibrium. So because that object is in equilibrium, all those constants here are going to be balancing each other out. So we're going to have mg is equal to KL when we're at equilibrium. And because those are all constants, mg is equal to KL throughout the problem. So that makes it kind of nice, because then in our differential equation, the right-hand side is just 0. So there is our basic model for all the spring mass problems. You're going to want to write this either on your formula sheet or you'll probably learn it after doing a few homework problems. And remember, this is for free motion where once the object is set into motion, there are no external forces. And we have a second order differential equation with constant coefficients. M, C, and K will all be constants. So these are the kind that we've been working on solving. We know that we expect to have two initial values to allow us to find a particular solution. And so often that is our initial position. And then we will probably have an initial velocity. All right, so we're going to look at several examples, and there's some vocabulary also in our notes, and I'll kind of go back and forth between the vocabulary and the example here. But these are the typical kinds of problems that we have in your homework. Sometimes they give you a little bit more information, sometimes a little bit less. But let's kind of look at what we have here. So we've got a mass of 0.2 kilograms, so that's our M value. It tells us that it stretches a spring 4 centimeters to its equilibrium position. So I'm going to have to be a little careful about units. Remember that our gravity constant is given in meters. So you want to use meters, kilograms, and seconds. Meters, kilograms, and seconds for your units there. So I'm going to have to be a little careful about that 4 centimeters and make sure I convert that to meters. That mass stretches that spring 4 centimeters to its equilibrium position. So that's the L that we talked about when the mass is attached to the end of that spring and it stretches that spring out. So 4 centimeters is 4/100ths of a meter. It's going to stretch that object down, so that's positive. The spring is then stretched 5 centimeters more. All right, so that 5 centimeters more from equilibrium and released from rest, that information is about your initial value. Our initial position is the 5 centimeters from equilibrium. Remember, y equals 0 is when you're at equilibrium. So if it's then stretched down 5 centimeters more, that would be a positive 0.05 meters. And since it's released from rest, our initial velocity, y prime of 0, is going to be 0 meters per second. All right, so we know that the basic differential equations model is m times y double prime plus c times y prime plus ky equals 0 for free motion, if we have no external forces acting on the system. We're given m, so that's pretty straightforward. But I don't have any values for C and K. So I do have enough information to find K. Remember that K is that spring constant. So some problems, they actually give you the spring constant. If they don't give you that spring constant, then you'll need to find that. You're going to use mg equals KL to find that K value. And so we have our m, we know g, 9.8 meters per second squared. We need to find k, and we have L. So if they don't give you k, they should give you enough information to find it, and that's how you're going to find it. Okay, so this is my value of k, so I now have that. And then the other issue here is damping or friction. So I wish the problems in our homework and our textbook in my math lab would actually say, assume no damping or assume a frictionless system or something like that, but they don't. So I intentionally typed this problem to not say anything about that, so it would model sort of what you're going to see in your homework. So it would probably be better if they would say, assume no damping. A lot of times when I write problems, so on written assignments that I give you or on exams or quizzes, we'll say assume no damping. But on your My Math Lab homework, if it doesn't say anything about damping, you're going to just assume that damping is 0. So that's really assuming an ideal frictionless system. When you work with these spring mass problems, you'll often end up with decimals for your coefficients. I like to multiply through by something to clear the decimals. So 0.2 is 1/5, so I can multiply through by 5, or 10 works nicely too. So whatever, I like to do that. That's up to you. But just to kind of be aware, you might have some sort of ugly numbers in these spring mass problems. Okay, so notice here that I get two pure imaginary solutions for my characteristic polynomial. And this is worth pausing for a moment here and just kind of realizing that anytime c is equal to 0, this is the kind of solution that you're going to get. Right? If you just think through the characteristic polynomial and solving for r, if c is equal to 0, you're going to get two pure imaginary solutions. So your solution to the initial value problem is going to involve just sine and cosine functions with some constants out front. All right, so that's my general solution. I do have initial values, so we'll go ahead and use those to find our C1 and C2. So when I put those in, y of 0 equals 0.05. This first equation is going to give me 0.05 for C2. Since sine of 0 is 0, that first term will drop out. Cosine of 0 is 1. So there's my C2 value. And then for the second one, when I plug my initial values into this one, I will have 0 equals 7 square root of 5 C1. Cosine of 0 is 1. The sine term will drop out, so I'll get C1 is equal to 0. All right, so at that point, I've got my solution to the initial value problem that it asked me to find. All right, so there is my solution in exact form. Some of my Math Lab homework will ask you for decimal approximations for your coefficients, so the time to do that would be at the end of the problem. If you do that too early, you can end up with compounded round-off error as you go. So if you want decimal approximations, you can do that here. And so I want to just talk a little bit about, like, what does this equation describe? So this is a pretty straightforward equation. Just to think about the graph of this equation, this is a cosine wave with amplitude 0.05. So the natural period of the cosine function is 2 pi, but this 7 square root of 5 that's here will change that. We'll make it oscillate faster. So the period, or the length of time it takes to make one oscillation, is going to be 2 pi over 7 square root of 5. So we'll take one cycle through that cosine wave in t equals 0 to 2 pi over 7 square root of 5 seconds for one oscillation. And we're going to just have continuing oscillations over and over again every t equals 2 pi over 7 square root of 5 seconds. All right, let's go look at some vocabulary that kind of describes that, and then in the next video we'll look at some more examples with some sort of different situations with damping and examine what's happening with those. Okay, so in the problem I was working on, my solution came out fairly simple. It had some coefficients that maybe weren't so nice, but there are a few homework problems where maybe your C1 and C2 values both come out to be non-zero numbers, and so you end up with a solution that looks a little bit like I have here in this trig identity, what I have on the left side. Some of the My Math Lab homework asks you to go ahead and rewrite that as a single trig function using this trig identity. So you'll want to put that trig identity on your sheet. It's not hard to use. You just need to use it. Some of the later examples we'll look at where we use it. I am not ever going to ask you to do that unless there's some reason in analyzing the problem that you need to do that. But there is some My Math Lab homework that specifically asks you to write your answer in this form. So the C comes from this equation here, essentially looking like Pythagorean theorem, right? And then the phi has to make both of these equations true. So sometimes that's a little tricky if you have negative values for A or B. You have to be a little bit careful about quadrants and inverse trig functions, but you just need to make sure that both of those equations are true to find your phi. Okay, so there's some vocabulary associated with the example we just looked at and then also the examples we will look at later. All right, the example we just looked at is what is called an undamped system. So sometimes they might not say there is no damping, but they will say you have an undamped system. So that is like what we just did here. We assume that C is equal to 0, no friction, and idealized motion. So that was example 1. And one important idea with that we talked about with example 1 is that you can kind of think through anytime C is equal to 0, you will end up with two pure imaginary solutions from your characteristic polynomial. And so your solution will be of the form C1 cosine of bt plus C2 sine of bt. Maybe you use that trig identity to rewrite them if it asks for that. But you're going to just get basically repeating periodic motion over and over and over again. Okay, so the next couple of examples after that actually do have some damping in them. And so if you do have damping, then you have one of these next three vocabulary things. So these all occur when C is not 0. So there is some kind of damping there. But basically you've either got a little bit of damping, a little bit of friction, a lot of friction, or this amount that's sort of exactly right and in the middle. So an underdamped system has a relatively small value for C, small enough that they will shrink the oscillations, but they will not completely stop. And that is what we will see in example 2. And when we do those, we're going to get values for the characteristic polynomial that are of the form a plus or minus bi, with a being negative. So your solutions will involve e to the at cosine bt and e to the at sine bt. And so your general solution is going to be made up of those two. Remembering that a is going to be negative. So what you're going to end up with is oscillations, but since a is going to be negative, you've got this exponential decay function that is going to control the amplitude on those oscillations. So we'll look at that in example 2. Overdamped system is when you have a large value of C. So that is going to be when you have friction or resistance enough that you don't even get any oscillations, just motion that's going to approach the equilibrium position. I'll just put 0 here for the equilibrium position. That's what we're going to see in example 3. And when you look at that, you're going to notice that you get R values that are real and distinct. So your solution is going to involve two exponential functions with your two R values here. And those two R values will both be negative, so these are both going to be exponential decay functions. So everything's going to just approach 0 as t gets larger. A critically damped system is when you have that exact right value of C where the system will switch from being underdamped to overdamped. We will look at that in a little bit later video here. So C is the specific value, a bifurcation value, that will cause the system to change from being underdamped to overdamped. So in practical terms, it doesn't really make sense that you're going to have C being exactly that right value. But the important thing is that it's where it switches from being underdamped to overdamped. When you solve that characteristic polynomial, you're going to get repeated real values. We don't have an example of that, but you have some in your homework where you get repeated real values for your characteristic polynomial. All right, these next vocabulary words are all really about trig functions, so I'm going to kind of quickly talk through those. Amplitude is the size of the oscillation, so just like in that last example, remember if you've got trig functions, that constant out front gives you the absolute value of that constant out front gives you the amplitude. So that is one reason perhaps to use that identity, both of your coefficients, your C1 and C2. If you don't have one of them becoming 0 like we did in that last example, you can collapse the two trig functions into a single one using that identity, and that C will give you your amplitude of your oscillations. Period, time that it takes to make one oscillation, one cycle. And so just like we saw in the example we looked at, that period is 2 pi over whatever that omega was. It was 7 square root of 5 in the example we looked at. Time varying amplitude and quasi-period, those have to do with problems where you actually have damping. So these would be when C is not 0. So we didn't see those in the last example. But these are for when I have oscillations that continue but decrease in amplitude. So we'll see that in example 2, where I have something like that. So it's not really a true amplitude because it's not a repeating sort of height on those oscillations, but you've got a time varying amplitude changing over time. So that's going to be controlled by that exponential decay function. So that's what's happening here in the green. And then a quasi-period, time to make one cycle. It's not technically called a period because it's not exactly repeating that motion over and over again, but it's found in the same way. T equals 2 pi over omega, and it would tell you from peak to peak what that time is going to be there. These last 3 words are sometimes used in physics problems. We don't really use them too much in our homework in this class, but you'll see them a lot in physics books. So I just want to point out that they are here. Frequency is cycles per second, so it's 1 over the period. So omega over 2 pi gives you the frequency. Sometimes you might put that in hertz or megahertz units. That omega is called angular frequency. It looks like a W, but it's really an omega. It's called the angular frequency. So we don't call it that too much. A lot of times we'll be focused on the period, so you'll use it to calculate the period. And then that phi is called a phase angle. That comes up in some circuits applications, often other kinds of physics applications. So we don't see that too much in our class here, but those kind of come from that trig identity that's up at the top there. All right, so try some homework and or watch that next video for some systems that have some damping.